Hi everybody, and welcome back to Precalculus. This is Mr. Gallagher, and today we are going to be talking about graphical approach to limits. So this is actually the topics that's covered in section 12.1 in your book, and we're going to look at bringing out some of the rational function graphs with holes and asymptotes, and also the idea of limits. So some of the things that we've been working on, kind of wrap them up all together. So I want to start by looking at this graph. And I have a picture here of the graph of f of x equals x cubed minus 8 over x minus 2. Now, of course, if you graph this, you can't have a value at x equals 2, right? Because that would be divided by 0. But it's not an asymptote, it's a hole, because actually if you factored x cubed minus 8, you'd get x minus 2 as a factor. You could cancel it. So it's a hole, not an asymptote. But what if we want to figure out what is the value of this function at x equals 2? Well, it doesn't have a value, but it has to get pretty close to something, right? So if I look at this value right here, where x equals 2, there's got to be a corresponding y value of where that hole is. And we can find it algebraically, but let's talk about finding it by just looking at the graph itself. And if we could look at some of the other values right around it. So I've got this chart here, and I'm going to plug in some values for x, whether it's 1.75 or 1.9. I'm going to get closer and closer to 2, but I can't plug in 2. And see if we can look at the graph and the values and see if that kind of gives us an indication. So if I plug in values, and I've already worked them out in my calculator, but you can plug them in yourself. If I plug in 1.75 for x into the function, I'm going to get that f of x equals 10.56. When I plug in 1.9, I get 11.41. Then I plug in 1.99, I get 11.94. I plug in 1.999, I get 11.99. I can't plug in 2, but if I plug in 2.001, I'm going to get 12.006. 2.01 gives me 12.06, and then I get 12.61 and 15.25 for the last two. So you'll notice that 1.999 gives me 11.99, and then 2.001 gives me 12.06. So I'm sure that you can kind of get an idea of what would x be, or what would f of x be if I could plug in 2. Where does that hole exist? Well, that hole exists at 12. So the hole is at the point 2, 12. And that's the value of f of x. The value of f of x is going to be 12. So we're going to be talking about this as a limit. So what we can say is, we can say that the limit of f of x as x approaches 2 is 12. So as x approaches 2, it doesn't actually equal 2, but as it gets closer and closer to 2, we can say the limit of f of x as x approaches 2 is going to be 12, or the limit of the whole function itself, right, equals 12. And that basically says what happens to y as we get closer and closer to a certain value. Some values don't have limits, and we're going to say that those limits do not exist as we approach a particular value. We're going to use the abbreviation DNE. So a couple of things, a couple of rules to keep in mind. When we talk about approaching from the left and from the right, when we talk about approaching, and we did this when we looked at limits for asymptotes, but when we talk about a value approaching, or the limit of f of x as we approach some value from the left-hand side, we are going to say, and I'm going to zoom in here, we're going to say as x approaches c minus, the limit as x approaches c minus of f of x, or meaning approaching from the left. And then likewise, we're going to look at what is the limit of f of x for some value c as it approaches from the right-hand side, and we're going to say that is as x approaches c with a plus symbol. And then those could be two different values, or they could be the same value. If we look at the overall limit at x equals c, we have to look at the left-hand side limit and the right-hand side limit. And if they're both equal, then we can say the overall limit of f of x as x approaches c is going to be whatever that value happens to be. And one other thing to bring up, and this is very important, is that understand that the limit as x approaches c of f of x, or f of c, they do not have to be the same thing. And we'll see some examples here to talk us through that. So let's look at these first ones. So here I've got a couple of graphs here. The first one, I've got, looks like a piecewise function. I've got a break in the graph. And we approach this value of 1, we approach it from the left-hand side and from the right-hand side. And so let's look at the overall value of those two. So what is the value of the limit of f of x as x approaches 1 from the left-hand side? Well, notice it's getting closer and closer and closer to, but does not actually hit 1. But the limit is still going to be, my y value is going to be 1. And likewise, what happens? That was when it approaches from the left. What about as it approaches 1 from the right-hand side? Well, as it approaches 1 from the right-hand side, as you see here, we actually get closer and closer to, and we hit 2. So the limit is going to be 2. We actually hit it. So the limit is the value that it approaches. In fact, f of 1, this fourth part down here, we're going to skip the other one for a second. What is f of 1? Well, it's where the closed hole is, right? F of 1 is going to be 2. But what about this overall limit as x approaches 1? Remember we said in order for the overall limit to exist right here, the f of x and the limit of f of x as it approaches from the left and the right have to be equal. Here they are not equal because the limit as f of x approaches from the left-hand side is 1, but from the right-hand side is 2. So the overall limit does not exist. So we're going to put DNE. Let's try another one. What about here? Again, the limit as it approaches from the left-hand side, from the left-hand side as it approaches 1, looks like we're going to hit at this point -1, so we're going to say -1. As it approaches from the right-hand side, it looks like f of x is going to be equal to 1, right, even though there's an open circle here. F of 1 is 0, right, because there's that closed dot right there. And again, does the overall limit exist? Well, it's different for the left than it is from the right, so we're going to say this limit does not exist. And I'll go through these, and feel free if you want to play them again and kind of rewind and hit those different examples as we look through the explanations. Let's try a couple others here as well. So here's another graph. It looks like we're going to look at as x approaches 1 again. As it approaches it from the left-hand side, it looks like we're getting up to 1. So from the left-hand side, it's 1. As we approach 1 from the right-hand side, again, this y value is 1. So now they match, right? So what is the limit as x approaches 1 overall? Well, that's going to be 1 because the left and right-hand sides match. But what is f of 1? This last problem here, what is f of 1? Well, there is no closed circle at 1. There's no value. F of 1 does not exist. So there's another situation. Let's try this one. Overall, it's the same graph, but I've got this closed circle down here. Well, does that change my limits? It doesn't. The f of 1 from the left is still 1. Limit as f approaches 1 from the right-hand side, still 1. The overall limit is still 1. But now what is f of -1? Well, that's going to, or sorry, f of 1 is -2. And that is the value for when I plug in f of 1, I'm going to get 2 because that's where the closed circle is. Let's try one more. What about as x approaches 0? So we're looking at this right here. Well, there's no break, there's no hole, there's no asymptote, there's nothing. All my values are going to be the same. As I approach from the left, as I approach 0 from the left and from the right, both of my limits are going to be 1. The overall limit is 1, and f of 0 is 1. So that happens to work out because there's no break in the graph, there's no hole, there's no asymptote or anything else. One last part to look at here. What if we have not a hole, but what if we have an asymptote? So we are going to say, what about the limit as we approach the asymptote? Well, the limits really don't exist, but we are going to say we're going to use infinity to represent limits that don't exist in this case for negative or positive because saying that there is no limit means that it could be infinity because we can never reach infinity to begin with. Again, so we're going to look at both positive and negative infinity in these next couple of examples. So here is when x approaches 2. So I'm looking at approaching 2. Whoops. I'm looking at approaching 2 from the left and from the right-hand side. As I approach 2 from the left-hand side, I'm going to go down forever. So that means my limit is going to be negative infinity. But as I approach 2 from the right-hand side, I'm going to go up forever and never hit that asymptote, so my limit's going to be infinity. Do those two limits match? They do not, so my overall limit does not exist. Can f of 2 ever exist? Nope, so that is also a DNE for does not exist. But this one's a little bit different. What if I approach -2 from the left and from the right? Well, you can see from the left and from the right, they're both negative infinity, correct? But since they're both negative infinity, then the overall limit is also going to be negative infinity because they're both equal. Sorry, negative infinity. And then what about f of -2? Well, f of -2 in this case, look, happens to have a dot or a closed circle right on -2. So we do have, or right at 0. So f of -2 is 0. There we go. I do want to talk about end behavior now just a little bit. So, and when we talk about end behavior, similar to what we talked about earlier a couple weeks ago, we're going to look at the end behaviors of the graph. So there's 5 possibilities. If it goes up forever, then we say the limit as x approaches infinity is going to be infinity, right? Or as x approaches negative infinity, we're going to say that's going to be infinity as well. It could go down forever. So as x approaches infinity, we're going to say that's negative infinity. This one happens to be up, so we're going to say negative, or this one, sorry, is positive infinity because it goes up forever. And then a couple other things that can occur as my end behavior. Here, as x approaches infinity, it looks like it's getting closer and closer to that asymptote at -2. And here, as x approaches negative infinity, it's getting closer and closer to that asymptote at 4. This one looks like as it goes to infinity, it's getting closer and closer and closer. It's oscillating back and forth, right? Above and below, above and below, above and below. Remember, horizontal asymptotes, you can cross horizontal asymptotes. So it looks like I'm getting closer and closer to that asymptote, which happens to be at 1. And this one's getting closer and closer and closer to this asymptote, which happens to be at 0. However, these two, this one here doesn't look like it's getting closer at all. It's just like a sine or a cosine graph that keeps going away. So it never approaches a limit. So we're saying this limit in this case does not exist. And this limit, even though it is getting closer, it's still going up forever. So we're going to say this limit here as x approaches infinity is infinity. So there's a couple other examples. I went through all those kind of without pausing. So feel free if you want to play those again. You can kind of look at the answers that we have, and I'll post these in the notes section for Precalculus as well. And that's it. We do have a worksheet that's associated with this lesson as well, and the worksheet is available to you on eCampus in the modules. Please make sure you, if you can print it out, great. If you just want to write your answers on a regular sheet of paper, that's fine too. Then make sure that you take a picture of your completed assignment and post it to the assignment section for this week's assignment. Thank you very much and take care.